All right, so let's start by looking at the handout from last Thursday. So if you find that handout, I think in books it's going to look like this at the very top. So if you go right into books, you'll do that. Otherwise, you can kind of go through the process of downloading it again. It shouldn't change anything. But it's the one from last Thursday. So it looks like this, but I'm going to be on page 3. And page 3 looks like this at the top. Just a couple of problems with a big blank space. And we're going to start at the bottom right here where it says the angle bisector theorem. And we're starting with this one because it's going to be very similar to what you are already familiar with. Okay, so let me know. Is anyone struggling to get there? Okay. So, angle bisector theorem. We are looking at a triangle with an angle bisector cutting through. So, visually, this should look very different from the side splitter. In fact, I'll go back to a side splitter real quick. All these well, not all those, but a lot of these right here are side splitter. Like on this page, E, and you don't have to go back to this. You can just kind of look at the screen. So, E, F, G, and H, those are all side splitter. And then you can see the difference. I and J, this is angle bisector. So visually, hopefully you can all see the difference. Everyone see that? Okay. That doesn't really change things too much, luckily. So some of you, because we had some angle bisector yesterday on the handout, so some of you might have tried that, I don't know. And you can learn now if you kind of thought through it correctly. So with this one right here, the way this works is that angle bisector will cut through the opposite side. So here's the angle being bisected up in the top left. It is cutting this opposite side proportionally to these adjacent sides. So the 6 and the 10, 6 is shorter than the 10. And notice right here when it cuts this opposite side, this 4.5 is shorter than the x. And it's shorter proportionally. All right, so let's go ahead and I just want you to intuitively try and figure out how we would solve this. So this is being cut proportionally. I'll just spot you this. We will be setting up a proportion. And just looking at this, your best guess of how would we set up a proportion in order to solve this, what is your thoughts? We've got 3 numbers and 1 unknown. Yeah. 6 over 4.5, that works. 6 over 4.5 equals what? 10 over x. There you go. So I hope that this is kind of intuitive. You might be sitting there thinking, I'm not sure if I'm doing this right, but I'm betting a lot of you are kind of just naturally assuming it should be set up something like that anyway. And maybe you just lack a little confidence right now. So yeah, this works. So here's what we're saying. The 6 right here is going to correspond, because that's the side length of our triangle. So this side of the triangle corresponds to this side of the triangle, the 10. And then this segment 4.5 corresponds to that segment x. So we have 2 segments that correspond to each other, and how we set up the proportion is kind of up to us. So let's just see if we can find one other way of setting up a proportion that works. So let's say we didn't want to do 6 over 4.5 equals 10 over x. What could we do instead? Okay, 6, I heard. Not that one, unfortunately. 6 over 10 does work. And we'll talk about, 6 over 10 equals what? There it is, 4.5 over x. So let's look at these two real quick. All right, so we're saying, in the first one, we're saying the side over its adjacent 4.5. So 6 over 4.5 is the side over its adjacent segment equals 10 over x, the side over its adjacent segment. So we're keeping the 6 and the 10 in correspondence because they're both in the numerator. Okay, in the next one, we're saying 6 over 10, so that's one side over its corresponding side. 6 over 10 equals 4.5 over x. So left to right over left to right. 4.5 over x. So let's kind of see what happens if we set it up in an incorrect way. So if we did 6 over x equals 4.5 over 10.
How come that's incorrect?
Okay, well, let's see. What corresponds to the 6 here is the 10. And if we're going to keep these in a good proportion, then we need to either set these into a ratio with each other, the 6 and the 10, like we did in the second one, or we need to make sure that they correspond and they're in the same relative position, both in the numerator, perhaps. So 6 and 10 can both be numerators, or they can be in a ratio with each other, but they can't be set diagonal from each other. So that doesn't work. And let's look at one more reason why this won't work out. I'm not going to go through and do all the math here, but if I just show the cross products real quick for all of these, and I'm not even going to write out an equation after this. I'm just going to circle all these. Look at the first two. What is 6 multiplying by? X. 6 times x in the first one, 6 times x in the second one. 4.5 times 10 in the first one, 4.5 times 10 in the second one. But now we go down to the third one, and what do we have? What is x multiplying by here? 4.5. So we're getting a different equation out of this, which is an incorrect one. And we're going to get 6 times the 10. Okay? So you can see why if you set up the proportion incorrectly, you're not going to get the correct answer. So remember, for correspondence to hold, then the parts that correspond either need to be in the same row or set into a proportion with each other, and it needs to follow the same pattern. So if I'm going left to right, 6 over 10, I need to do 4.5 over x, which is kind of what we did with the second proportion here. So let me go ahead and erase this one at the bottom so you don't get confused, because that one is no good. Either one of these works, and you can now go through and you can solve the proportion for x. Has anyone done that yet? Well, then let's do that together. We get 6x equals 10 times 4.5. What's 10 times 4.5? Okay, 45 equals 6x. We know what to do here, right? Just divide by 6, and what does x equal now? 7.5. There it is. And again, you can always double check this. If you plug this 7.5 back in, I'm going to put a box here so that this is where I'm checking. So I have 6 over 4.5, I'm using the first proportion, equals 10 over 7.5. And I can divide both of those and make sure I got it right. And they should both equal 1.3 repeating. Okay. So as long as we have the same decimal when we do the division, then we've done it correctly. All right, so is this angle bisector making a little bit of sense? Yes. Okay, hopefully a lot of sense. But we'll see if we can build up to that. Okay, so what I did here is if you get out a markup, go to the previous page in the same handout, you'll see down at the bottom right, you'll see these two problems that are both angle bisector problems. So what I want you to do, first of all, is just take 30 seconds, a minute, whatever's needed, to write out your two proportions. If you've got your two proportions written out and you have time, you can go ahead and finish solving it. But for I and for j, go ahead and write out a proportion that will work so that you can solve for your unknown value. All right, and there can be multiple proportions. So I'm going to ask someone to tell me what they wrote down. And Yours might not look the same, but you can make sure that yours works just by looking at the cross products. The cross products should still be the same if you set it up correctly. Okay, so someone tell me for I how you set it up. 6 over 4 equals 9 over x. Okay, you might have set it up the same way. This is correct, but look at your cross products. If you have 9 times 4 equals 6 times x, then you set it up correctly. All right? Now, someone different, tell me what you did for j.
Okay. So 6 divided by 10 equals x over 8.
Okay, 6 over 10 equals x over 8. Oops, not x over x. X over 8. So again, that one does work. This is correct. If yours doesn't look like this, just check your cross products. You should have 8 times 6 and 10 times x. If you did that, then you're good. Yeah. Yes, as long as your cross products, again, so I'll just kind of write this out real quick. So the cross products for the first one, my next step is going to be something that looks like this. So as long as your next step looks the same as that, then you set up your proportion correctly. And like I said, there's many ways of setting up the proportion, but you set it up correctly if your next step looks like that. If your next step on this one looks like this, where you have 10 times x equals 6 times 8, or you might have already done the multiplication out, then you did it correctly. So what is the answer for I? 6, and the answer for x is 4.8. That's it. So, any questions? All right. Then what you'll need to do at this point is you'll need to go back. If you haven't downloaded it yet, you'll need to go to the Google Classroom, get the Theorems Practice number 1. If you already downloaded it into books, you can go ahead and get that. And we are going to be going to page 5 of Theorems Practice 1, which looks like this. To us pretty quickly. Okay, so we're looking at an entire page that is just angle bisector. Now, I do want to mention that this, and like we've already talked about, the angle bisector doesn't change our approach too much from side splitter. We're looking for a pattern of correspondence. Okay, and we're kind of seeing how to find that pattern with angle bisector problems. I want to kind of mention something real quick as far as you're going to be looking at a diagram. You're going to have to determine, is this mid-segment theorem, is it side splitter, is it angle bisector, or is it the fourth one that we're about to talk about? And when you're looking at those, I want you to remember that only mid-segment is set up to be a little different. And we're going to go back to mid-segment, go back over all these theorems again. Mid-segment is, we'll kind of approach it differently, but everything else we're using proportions for. So if you know how to set up proportions and you're comfortable with that concept, then that's going to work for 3 out of the 4 theorems that we're using. So it hopefully doesn't get too confusing with that. All right, so let's look at this. And most of this is pretty straightforward compared to the problems you just looked at. So you can just get some practice. But I wanted to look at just one of these, and I picked out number 8. Not that it's especially difficult compared to the others, but it's we can see there's something a little different going on in this problem. We want to solve for the length of that entire side, and how are we going to be able to do that? What's that? There we go. All we need to do is solve for, if I called this right here x, if I solved for x, and I considered it like any of the first 4 problems, then once I got those 2 numbers, what do? Yeah, just add it up. All we're doing for a problem like this is adding one extra calculation, one extra addition problem. So I'm not going to go through and solve this, but you guys have a little bit of time. Just make sure you're practicing with this. I'm not giving you the rest of class 25 minutes to do this because it shouldn't take you that long. So I'll just come around if you have questions, but practice with angle bisector for a while. Okay, so when you're looking at these diagrams right here, this looks very similar to what? So we've learned about mid-segment, side splitter, and angle bisector. What does this look very, very similar to? Okay, well, it does look like dilations, and this might look also similar to your side splitter theorem. Okay, there is a difference here, and we're going to notice it in just a second. You might already notice it. I'm going to go back real quick to the previous page, and notice that these problems, not the ones at the bottom right, but everything else here, this is side splitter. In fact, this one in the bottom left. Well, let's ignore that one because there's a little bit of confusion there. But this one E right here, that is side splitter. And we know it's side splitter because here's the key difference. All of the lengths given are along the sides of this triangle. If you consider this big triangle right here, all the lengths are along the side. Okay, so I'm just going to highlight real quick. X plus 4, 16, 8, and 12. Those 4 are along the sides. Now, I'm going to go back to the other one that we were just at. And notice now, this isn't side splitter because if it was, we'd have a 7 and a 14 right here. And then we'd have measurements over here. But we don't. What we have instead are measurements along the parallels. So what I want you to do is just tell me initially how you would maybe set up your proportion. Or let me just say this. Don't be afraid to be wrong right here. What seems to make sense based on what we've been doing so far? 7 over 5 equals... Yeah, and you know what? I completely agree. This seems to make sense. This follows the pattern we've been looking at. But this would be wrong. Okay? So what you have to notice is the difference here is that the distances given are along the parallel lines. So what we're looking at here, I don't have a better name for this than just calling this similar triangles. All right, so I'm not calling this a similar triangle theorem, but it's just similar triangles. And we're going to see how we solve that. So if we went and did this right here, this math, we're going to get 14, so 7 over 5. Our x value here, if we solve this proportion, we're going to get 10. And that is not our answer. X does not equal 10. So let's see why this does not work. What I want you to notice about this diagram is that we have 2 triangles, one of them nested inside the other. And so a minute ago, Kevin, when you said dilations, yeah, that's really what we've got going on. We've got the small triangle being dilated out to be the bigger one, or you can consider it in reverse. And the best method I can tell you for this is to notice that you've got 2 triangles, and I need to draw these triangles separately. So now I'm going to have a small triangle right here and a bigger triangle. And just separate the 2. Break them apart. And if I do that, I'm going to add in the distances that I know. So for the small triangle, I think we'd all agree this side is 7 and that side is 5. All right. We also probably all agree that for the big triangle, x goes down here. So my question for you is, what is the length of that side on the left for the big triangle? Not 14. It's 21. It's 14 plus 7. It's that total length of 21 centimeters. Okay. So look at what we've done here. We've taken this diagram and we split it into 2 triangles so that we can see the true relationship, the true proportion that's going on. And let's go ahead and use your intuition now to set up your true proportion. So how should we set up our proportion in this case? 21 over x equals 7 over 5. And you can see the difference here. This is the incorrect one. I should put a red X through this real quick. But 14 over x and 7 over 5, well, that is close, except that instead of 14 over x, we should really have 21 over x. All right, so I'm going to go ahead and cross this one out. No. That is very bad. So it's good if you have that written down, and now you can actually show, put the big X through it. Say, no, that is not the correct way of solving it. And now we can see we need to split this into two triangles. In fact, I'm going to add a little note to that effect. If you're going through and solving the proportion right now, that's fine, but make sure you're writing down a note. So split into two triangles. And this is the key part. When lengths are along parallel lines. All right. So solving the proportion, how many of you already did that? Can anyone tell me the answer?
15.
Okay, so we do have our correct answer here is x is going to equal 15. I'm not going to go through the steps of that. You guys can do that on your own. Okay, so again, I just have to draw this comparison. I'll leave this up for a second so you can copy it down. But we need to see the comparison between this situation, which I'm calling similar triangles, and the other situation, which we call side splitter. All right, Kyler. All right, so I'm going to go back to the very first page of this. Let me find a good example. Okay, so this one right here. You don't have to go back, and you just need to look at the board and see this. You can see the difference right here. In problem number C, we have all these parallel lines. No distances are given. Okay, we're not looking at lines at distances along the parallels. So I can just set up a proportion with the numbers like we expect. 6 over 5 equals x over 4. That one works. But then if we go back now to this page, we look at it, we're being very critical or how we're looking at things, very observant. And we're saying, oh, this is a 6 and an x along parallel lines. So now I need to think of this as similar triangles that are nested inside one another. Okay, so now draw these two separately. So the small triangles, what's the left side? Eight. So we have 8 centimeters on the left. What about the bottom? 6 centimeters. The left side of the big triangle is 14. And the bottom is x. There you go. So now you can set up a proportion. Let's just set up the proportion. I'm not going to take the time to go through and solve it. Tell me what proportion we could write down for this. Equals 8 over 6. There you go. Again, not the only way you could set up that proportion, but your cross product should be the same. It should be 8 times x equals 14 times 6. And anyways, there you go. I'm just going to draw a line to distinguish those two. So once you've gone through, if you're understanding those two problems, notice the back page of this handout. And I'm just going to show it to you, but I'll give you guys the remainder of class, which isn't much, just to practice with these. Focus on the first 3 on the back side with the time that you have. If you want to keep going, you can. But I'll tell you, problem F is a little bit more challenging. If you jump straight to that one, it's going to be a little bit difficult. So try these 3 problems on the 4th page of this handout, and moving on if you have time.